Okay, welcome to Robotics 2. In this class, we are going to talk about the important coordinate systems. Coordinate systems, they are similar to the coordinate systems that we studied in Robotics 1. There is always an inertial coordinate frame, the coordinate frame that is fixed. In the case of Cartesian robots or in the case of articulated robot, usually inertial frame is the very first frame or the first joint that we use to analyze the kinematics of the robot. In the case of the aerial robots are flying. So what we assume is we assume a flat earth. We assume the earth is flat, and what we do is we have earth-centered coordinate frame. So that coordinate frame is earth-centered coordinate frame. The difference between the coordinate frames that are used for aerial robotics and for the Cartesian or the articulated robots is we always use something called as north, east, down. So think about it. You have, this is the north, that's east, and you have down. North is X, east is Y, and Z is down. So always we have something called as north, east, down. And the reason we have the down vector or Z vector going down is to facilitate gravity, because gravity is aligned with the down vector. So in this first class, I'm going to talk about the coordinate system. We are going to use the right hand coordinate system. So curl your fingers, right hand fingers, in the direction of rotation. If your thumb is pointing toward the axis, that rotation is positive. Attitude means the angles. And in robotics 1, we also talked about the angles like roll, pitch, yaw. Same angles are used in the case of aerial robots. These angles are represented with different techniques. There is something called as the Euler angles, roll, pitch, and yaw. Those are Euler angles. There is rotation matrices. Remember the rotation matrices 0R1, 1R2, 2R3 that we studied in robotics 2, robotics 1. Same rotation matrices would come and play a significant role in the mathematics and analysis of kinematics. Then there is an efficient representation which is called as Quatonians. Quatonian representation is called axis angle representation. I will give you an introduction to Quatonian, but there is a fantastic webinar by 3 Blue 1 Brown on YouTube that talks about the Quatonians and the geometric representation and interpretation of Quatonians. The advantage of Quatonians is we will work through the math that Euler angles have singularities. Rotation matrices, they are big, the size is bigger. Quatonians are a very compact representation and they are free from singularities. And we will talk about what is the meaning of the singularity and how that singularity comes in the picture when we try to solve using Euler angles. So first and foremost, remember the right hand coordinate frame. We are always going to use the right hand coordinate frame. And in the case of aerial robots, we will always use north, east, and down. So north is going to be X, east is going to be Y, and down is going to be Z. So it's going to be always like this. So, and once again, I know we discussed same thing in robotics 1, but please understand, this is the right hand, this is X, this is Y, this is Z. X, Y, Z. Now we are going to use north, east, down. North is X. This is Y, and this is Z. So north, east, down, north, east, down. So right hand coordinate frame, north, east, down. That is the same coordinate frame. Curl your fingers in the direction of rotation. if your right hand thumb is pointing in the same direction as the arrow of the axis, that rotation is positive. Now, when we talk about aerial robots, there are two important coordinate frames that we need to study. The first coordinate frame is something called as Earth fixed coordinate frame. So basically, this is Earth fixed coordinate frame. And then there is this ABCF, which is called aircraft body coordinate frame. Craft body coordinate frame. Now, what is the difference? Typically, when we are going to study the UAVs, we don't expect them to fly in space. So usually they will be in the atmospheric region. So what we do is we actually make an assumption which is called as the flat Earth. We assume that the Earth is flat. And then on this flat Earth, we have this north, east, down. This is the frame that is fixed onto the flat Earth. And then you can have an aircraft or a quadcopter or a UAV or some other exotic flying object, and you can add its own coordinate frame. So you would have north, you would have east, and you can have down. So you can have its own coordinate frame. This coordinate frame is A, B, C, F, and this is E, F, C. So these are the two coordinate frames. Now, how these two coordinate frames are related to each other. And I want you for a minute to think about the similar analysis that we did when we were studying robotics 1. Remember, we had one joint here, then we had one joint here, then we had maybe one joint here, and then this was R, R, R. And when these three revolute joints were perpendicular to each other and co-located, this is very important. When these three revolute joints R, R, R were perpendicular to each other and co-located, that formed something called a spherical wrist. So now I want you to visualize that there is some sort of a spherical wrist between the Earth fixed coordinate frame and aircraft body coordinate frame. In other words, there are three rotations that take the Earth fixed coordinate frame to the aircraft body coordinate frame. So think about it like there are three revolute joints here, R, perpendicular to R, perpendicular to R, that relate this Earth fixed to aircraft body coordinate frame. And these rotation angles, they basically are, they get involved, or we use those to find out the Euler angles. So these are the rotations. So what you do is you have Earth fixed coordinate frame, you rotate that along yaw, then you rotate that along pitch, and then you rotate that along roll, and then you land up with the aircraft body coordinate frame. And I would actually talk about this in little bit detail. So think about it like initially you have this Earth fixed coordinate frame, and what you want to do is you want to go from Earth fixed coordinate frame to aircraft body coordinate frame. earth fixed coordinate frame to aircraft body coordinate frame. So this transformation is achieved by means of three successive rotations. What are these rotations? The first rotation is the rotation about yaw. Then you have the rotation about the pitch, and then you have the rotation about the roll. Now, I need to clarify. This is a particular sequence of rotation that will take you from earth fixed to aircraft body. So these two coordinate frames, this is a sequence of rotation. There are 12 such sequences of rotation that will take you from the initial frame to the final frame. And as far as we are concerned, we are going to stick to the same yaw, pitch, roll type of rotation. And these rotations will come again and again. And as long as we are consistent, our answers would be the same. And so you have psi, you have theta, and you have phi. This angle is called psi. This is theta. And this is called as phi. So you have rotation about yaw, rotation about pitch, and rotation about roll. Now the question is, how is this get defined in terms of a quadcopter? Now in terms of quadcopter, and I will actually show it to you first in the case of a fixed wing aircraft, and then I will show it to you in terms of a quadcopter. So let me draw a fixed wing aircraft. So this is the fixed wing aircraft. This is north, this is east, and this is down. So north is x, east is y, and down is z. So north is x, east is y, down is z. Now what we want to see is we want to see the rotation angles. So the rotation about down is yaw. So this rotation is yaw. And please note, curl your fingers in the direction of rotation. If your thumb is pointing towards the down axis, that rotation is positive. So this is yaw. Now rotation about east or rotation about y is pitch. So curl your fingers in the direction. This is pitch. And then curl your fingers about north, and that actually gives you the roll. This is yaw, pitch, and this is roll. Everyone understood this? Now, how does this change in the case of a quadcopter? So for quadcopter, yeah. Did I make a mistake here? Okay. So in the case of quadcopter, now I want you to look at this view of a quadcopter, and clearly there is no front or back. Depending upon what you choose, it's going to be the front. So let me see. This is x, this is y, this is z. So you have north, east, and down. And now you can actually use the same question. Yeah, just a second. So basically what you do is, I'm just showing you for the plus. If you have x, you'll have it something like this. The only difference in x and plus is when you are actually going to control the prop speeds, you have to make sure that you're actually controlling the roll, pitch, and yaw accordingly. But let's start with this configuration that is shown here. So here again, this is pitch, this is yaw, and this is roll. So that is the coordinate frame. And please understand, quadcopter is kind of you arbitrarily assign what is the front and back. Some of these new quadcopters, they also have something called as the headless mode. So for an example, whatever is the orientation, you can assign that orientation to be front, and the quadcopter will fly in that orientation. But as far as our dynamical equations are concerned, we would actually derive those dynamical equations in north, east, and down. And please understand that the coordinate systems are very, very important, because if your coordinate systems are not aligned, then your answers won't be correct, your signs won't be correct. Now, at this point, I want you to visualize what would we mean by the yawing motion of the quadcopter. So you have this quadcopter, and yawing means the quadcopter is rotating in the horizontal plane. What do I mean by pitching of the quadcopter? The pitching of quadcopter means around the east axis, the front is going up and the back is going down. What do I mean by rolling? Rolling means, positive roll means the right hand side is going down, left hand side is going up. Everyone understood this? Now this sequence is very important, because how are we going to control the roll and pitch of the quadcopters? We only have control over the motor speeds. Out of these, two motors are going to rotate in clockwise direction, two motors are going to rotate in counterclockwise direction. By adjusting the speed or the rotation rate of the motor, you adjust the thrust. And depending upon the differential thrust, basically you would have either rolling or you would have pitching. So basically roll and pitch, you would be controlled for plus configuration for adjusting the speed of the motor. So these are the definitions of Euler angles, and these definitions of Euler angles are given in terms of the fixed wing aircraft that we just talked about. You have something called as the pitch angle, you have something called as the yaw angle, and you have something called as the roll angle. Now, I want you to visualize something like this. Remember when we talked about the spherical wrist in robotics 1, we talked about a case wherein two joints, they get aligned such a way that 1 degree of freedom is lost. So what happens then is, let me give you the same example again. Imagine that you have an aircraft. This is an aircraft. Let's redefine what is roll. This is roll, this is pitch, and then basically this is yaw. Do you agree with me? Roll, pitch, and yaw. Now imagine it's just a Boeing 747. It's going to fly at angle of attack 15, 20 degrees. But if it's an F-16, what's going to happen is, initially it will fly at 15 degrees. So again, check this out. This is yaw. This is yaw. It will again start flying. And after some time, at 90-degree pitch, please note, it has lost its yaw. Then you see that it has just lost its yaw. Its roll and yaw, they have become one. So in other words, we have lost 1 degree of freedom of that aircraft. That is called as the gimbal lock. The gimbal lock also occurs in the spherical wrist when the two joints, they get aligned, their axes get aligned, and basically you don't have control over one joint. And what do I mean by you don't have any control over the one joint? Which means whether you supply yaw command or whether you supply the roll command, the joint, the same thing happens. You don't have articulation in two different axes. You just have articulation in only one axis. That is the problem with Euler angle representation. That's why what we do is we use either direction cosines or rotation matrices, or we use the Kutonians. So, any questions here? Yeah. So basically, the regular aircrafts, they do not fly at 90-degree pitch. If you have the fighter planes, or maybe if you are doing some aerobatic maneuver, then they fly at 90 degrees. And then again, the flight, basically, it's a, they don't call it a roll, or I think they call it a nose dive or nose up. Basically, they don't call it a roll. They just say the aircraft is going nose up or going nose down. And basically, at that time, there are two ways that can be handled. You would have the singularity at 90 degrees. So basically, you have a software limit. Like as soon as you get division by 0, you say that angle is maybe 89 degrees or 87 degrees or 91 degrees or 92 degrees. That is something you can take care in software. Or otherwise, what you do is you perform the integration, differential equation motion, you integrate in Kutonians, not in Euler angles. And then when you try to find out the actual value, only that time you convert the Kutonian to Euler angles. And all this will be very clear to you. It will be very clear to you when we actually perform some MATLAB simulations, and I will share the simulink files that I have written, and we can actually run the simulations and we can see the aircraft is going 90 degrees up, 90 degrees down, and that is where the singularities come in the picture. Yeah. So does the system move with the center? Okay. Earth centered coordinate frame does not move with the aircraft. It's an inertial coordinate frame. Body fixed coordinate frame will move with the aircraft. Now, I need to clarify this, how this transformation takes place. You have Earth fixed coordinate frame. This is inertial coordinate frame. It's not moving. After Earth fixed coordinate frame, there is a vehicle 1 coordinate frame, which is the yaw rotation. Then there is a vehicle 2 coordinate frame, that is the pitch rotation. And then there is a vehicle body coordinate frame, that is the roll rotation. So, and I will derive this equation. So bear with me. So think about it. You have 0R1, 1R2, 2R3 that relates 0R3. Are you with me so far? And I will derive those. Just bear with me. So, but at any rate, 0R0 is going to be fixed to the Earth, and our Earth is flat. That assumption you need to violate if you have a missile, because missile is gonna go outside. So basically, you can't use a flat Earth assumption. You have to use a circular Earth assumption, and then the Earth models would be different. At this point, there are two important questions that come in the picture. the first and foremost important question is, how do I relate a vector in the aircraft frame to the inertial coordinate frame? What that means? So I have started at Earth's fixed Earth-centered coordinate frame. That is the flat Earth coordinate frame. That aircraft is going to move. So that aircraft is going to travel in its own directions. Like aircraft is going forward, aircraft is going up, aircraft is going down. But for me to know, I need to know in one constant coordinate frame how far that aircraft has traveled. I cannot determine the aircraft travel in aircraft's own coordinate frame. Think about like GPS. I need to know this is my 000, how far the aircraft has traveled with respect to this fixed coordinate frame. This problem is resolving the aircraft vector. It could be a position vector, it could be a velocity vector in the inertial coordinate frame. Everyone understood this? And we have solved this problem. This is exactly same as finding the position and velocity of the end effector, finding the position and velocity of the end effector with respect to inertial frame. Remember all the mathematical jugglery that we did in robotics 1? Same thing, same problem. Second problem is, I want to find out the angular velocities of the aircraft. Now this problem needs little bit of discussion. So think about it. You have this aircraft. Initially it was stationary. Both the coordinate frames were matched. Aircraft coordinate frame and Earth fixed coordinate frame were matched. Aircraft took off and then it performed some maneuvers and then it had its own velocity. Now its own angular velocity is in its own coordinate frame. It's a body velocity. So aircraft is rolling, aircraft is pitching, aircraft is yawing, but that velocity is measured in that aircraft coordinate frame. I want to know what is that angular velocity with respect to the inertial coordinate frame. Everyone understood this? So that is the problem of determining attitude, which is roll, pitch, and yaw, and attitude rate, which is roll rate, pitch rate, and yaw rate. Remember, this is the same exact problem that we solved when we were trying to find out the angular velocity of the end effector. Remember in robotics 1, we found out the angular velocity of the end effector. How did we find out the angular velocity of the end effector? Remember the Jacobian and all that stuff that popped in? So we are going to use the same concept to find out the kinematic parameters of the aircraft. And I would derive these. Okay. So here is the classic problem. The classic problem is, we are given the aircraft, and this part is very important because I'll tell you what is the most important part that you have to understand. Once you understand the coordinate systems, once you understand the transformation, once you understand how to go from the body frame to the inertial frame, your equations of motion would be very straightforward. Those are like Newton's laws. Like you have force is equal to mass times acceleration, and T is equal to I times alpha. And you just include all the aerodynamic and other forces that would make the right-hand side of those equations very complicated. But other than that, the important part that I want you to understand here is you have this aircraft. And this aircraft has its own angular velocities. So this aircraft is rotating something like this. And I have this Earth-centered, Earth-fixed coordinate frame. And I want to find out what are these angular velocities, PQR. What does it resolve into? Roll rate, pitch rate, and yaw rate. So what are the inertial rates? Inertial rates means roll rate, pitch rate, yaw rate. What are the inertial angles? Which is the roll angle, pitch angle, and yaw angle. Everyone understood this? Those are two important things that we have to find out. So the question that we are going to solve in today's class is, how do we find out the roll, pitch, and yaw? And how do we find out the roll rate, pitch rate, and yaw rate? So here is the equation. And the next slide, I would actually I will walk you through the MATLAB script. And if you have MATLAB, please open MATLAB, because I'm going to walk you through this. So theta dot, capital theta dot, these are the angular rates, those inertial rates. There is a rotation matrix W multiplied by the body rates. Body rates means the aircraft roll rate, pitch rate, yaw rate in its own axis. And the relationship between these two is given by that matrix. And please understand, again, theta is equal to 90 degrees. That problem pops up whether you find out the attitude or whether you find out the attitude rate, because you are going to get cosine of 0, 1 divided by 0 singularity. What it means is at 90-degree pitch, you cannot resolve the attitude rates. Now, what I want to do is I want to go to the very basics of what we talked about. Yeah.
So in this omega HP, these are all.
So B stands for body. B stands for body. B stands for body. Aircraft has its own coordinate frame, body fixed coordinate frame, that is traveling with the aircraft. Omega xb is the angular velocity about aircraft's own x. Angular velocity about y, aircraft's own coordinate frame, and z is the angular velocity about aircraft's own coordinate frame.
And the capital theta, that's with the ground, right?
Okay. Yeah, okay. And what I'm going to do is I'm going to draw this over here, because that's an important question, and I'm going to use this in the next discussion. So let's start with the flat earth assumption. Okay, I have a north, east, down coordinate frame. So I'm going to say this is my north, this is my east, and this is my down. This coordinate frame is fixed. Now I have an aircraft, it could be a quadcopter. I have an aircraft which is somewhere over here. And this aircraft, there is a coordinate frame fixed to the aircraft. So this coordinate frame is fixed to the aircraft. This is its north, this is its east, and this is its down. Clearly, this frame and that frame, they are not aligned. Do you agree with me? Now, what I'm going to do is, there are 3 rotations. So there is one frame here. There is one frame here. There is one frame here. And there is one frame here. So from this frame to this frame, you have psi. From this frame to this frame, you have theta. And from this frame to this frame, you have phi. So in other words, think about it like this is my 0th frame, 0. This is my first frame, second frame, third frame. So you agree with me, I'm gonna have 0R1, the rotation matrix here. I'm gonna have 1R2 rotation matrix here, and I'm gonna have 2R3 rotation matrix here. You agree with me? And these rotation matrices are exactly similar to the rotation matrices that we derived in robotics 1. The only thing that we have to make sure that the axes are aligned perfectly. Everyone understood this? This problem is similar to the problem of spherical wrist. So you have one, then you have second one, and then what you have is you have the third one. So this is R, R, R. This is your 0th frame. Now the difference here is, remember when we were drawing the coordinate frame for the articulated robot, we used 4 rules. Remember 4 rules that we used? Z-axis has to pass to the center joint. Z-axis has to pass to the center joint. Z-axis has to pass through. Z-axis has to pass through. And yeah.
So for roll pitch and joint, why do you have to compare it to ground frame? Why not compare it to the previous frame? It solves the singularity, right? Like previous frame, like always it moves on.
So what I'm doing here is, this frame is rotated by psi. This frame is rotated by theta, and this frame is rotated by phi. What it means is when I construct the rotation matrix, this rotation matrix would have psi as the joint variable. This rotation matrix will have theta as a joint variable, and this rotation matrix will have phi as a joint variable. Yeah.
There's a question on Zoom.
Okay. Yeah, you can't see anything on the whiteboard. That is correct.
It's simple. So it's a filter.
Huh?
It's word filter. So it blurs your background. I think that's on.
Okay.
None. It is on none, but maybe it's the camera itself.
Okay. Yeah. So all right. So what I would do, just bear with me if there are any other questions. Okay, I'll try to redraw this on here. Just bear with me. So you have this frame, and then you have this aircraft, and the only point that I was trying to make is this is similar to the revolute joint. Then you have another revolute joint, and then you have another revolute joint. Now, if you recollect, the roll pitch yaw here is the same thing as we did in robotics 1. So you have the rotation matrix. You remember the basic structure of the rotation matrix from robotics 1? So if you have, let's take a step back. So the first rotation is yaw. So do you agree with me that rotation is about z-axis? Second rotation is about pitch. Do you agree with me that rotation is about y-axis? And the third rotation is about roll, that is the rotation about x-axis. Remember? You remember this? Now, I want you to tell me the rotation matrices when you have a rotation about z. So what is the rotation matrix when you have the rotation about z? What is the rotation matrix when you have rotation about y? And what is the rotation matrix when you have rotation about x? From robotics 1, everyone understood that this is the z is the most common rotation matrix that we use. You agree with me? Which was something like cosine psi, sine psi, 0, sine psi, cosine psi, 0, 0, 0, 1. Remember, this is the rotation about z. Rotation about y is cosine theta, 0, sine theta. This is the rotation about y. So remember, here is going to be 0, 0, 0. Then you are going to have minus sine theta, cosine theta. And then you have the rotation about x. When you have rotation about x, so you are going to have 1, 0, 0, 0, 0. And you are going to have cosine c minus sine c, sine c, cosine c. So now, if I want to find out the total rotation, what I do is I multiply Rz, Ry, Rx. And what I get is this combined rotation matrix. And this, rotation matrix relates the inertial frame. So you have, this is in, so if you think about it, this is inertial and this is body. Yeah, question?
I still didn't get where theta, capital theta comes into the play.
Capital theta,
Yeah, so that's slide 10.
slide 10.
Yeah.
So capital theta is roll, pitch, yaw.
It's not a physical attribute. It's not a physical. Why is it comparing to? It's like in the previous diagram that's drawn on board. It's nowhere to be seen. It's not a physical attribute, right? Capital theta is just a matrix.
Yeah, capital theta has 3 parts. Capital theta is a vector. Capital theta, so you have, let me show you something like this. What this means is you have roll rate, pitch rate, yaw rate. That is a matrix multiplied by the P, Q, and R, which is the body angular rate. So body rates. And these are the inertial rates. Yeah.
So K3, N2, and B1 are those things 0 or 1, the equivalent of that, right?
Right. Basically, they are the transpose. So basically, the difference here is this is body, and that is inertial to inertial, right? But if you look at the way we studied in robotics, we always had inertial angular velocities on the left hand side. We had a rotation matrix, or we had a Jacobian transformation, and the body angular rate on the other side. So that's what is this. So I would encourage you, if you have a minute, you can run this code. You have R psi, R theta, R phi. Run this inside the MATLAB, and then you are gonna get this big expression that is the same rotation matrices that gives you the transformation from body to inertia. I'll spend a minute here. Just please understand that this transformation, you're gonna see it again and again and again and again. But this comes from the basic fundamental robotics 1 concept. You have 3 rotation matrices. The first rotation is about z-axis. Second rotation is about y-axis. And the third rotation is about x-axis. So you have rz multiplied by ry multiplied by rx, and that gives you this big direction cosine matrix that is 9 by 9 matrix that is shown over here. Any questions? Yeah.
So why do we not compare it to the
Previous frame?
previous frame of the UAV rather than the ground frame?
Okay. Previous frame of the UAV, it's somewhere floating between the current frame and the ground frame. The only frame that we know is the ground frame. We know where the ground is. We know that's our 0, 0. What I want to know is, I want to know where the UAV is with respect to the inertial or fixed or the known frame. Previous frame is floating somewhere in between. So I don't know where that frame is. That's why that is something for the dead reckoning. So to know exactly, it's like GPS. GPS is always give you latitude, longitude based on Earth center, Earth fixed coordinate frame. And then you can actually use the transformations and find out the vehicle velocity, vehicle acceleration, and all other properties.
So then what about the when drone goes to unknown location? Something like that.
Huh?
When drone goes to an unknown location.
So drone goes to unknown location. So what do you mean? The drone lost? Or?
Yeah, maybe. Like something.
So typically, when we try to look at the navigation and tracking type of this problem, we have a map of the environment. So for example, if I have the map of this room, but if the drone flies outside the room, then probably drone has gone outside location. So I don't have any map. I don't know where the drone is. So you just like GPS, the entire Earth is mapped. Like I have inside mapping. Any other question? Okay. Okay. So now this is the exact same map. And if you are following the textbook, this is the map that they have given in the textbook. But there is a difference. And I want you to know the difference here. The signs are reversed. Why the signs are reversed? Because please understand, the way we have derived is we have inertial on the left and body on the right. Inertial on the left and body on the right. But when in the textbook, that has body on the right and inertial on the left. So basically they flip. So that's why what you have to do is you have to perform the transpose of the transformation. But the answers are the exact same. So if you want to follow the textbook, I want you to note that his matrices are transposed because basically he is going from body to inertial. So just make sure that. But at the end, your answers are going to be the same. And if you don't believe me, here is the answer that he found. And let me talk about this notation. This notation is, you have R, E, B. This notation, you should read something like, just like what we did in robotics 1. This is R, E, B, which is 0, R, 3. This is the inertial or first frame or zeroth frame, sorry, inertial or zeroth frame, and this is the third frame. So to go from R0, R3, you will go 0, R1, 1, R2, 2, R3. And these are the matrices, the rotation matrices that come over here. And please note, this matrix is the same matrix that we derived. And as you can see, this is the matrix that we have derived. So the concept that we studied in robotics 1 are going to be applicable in robotics 2. And this is something that you did in robotics 1. Say, how do you find out the angles or the attitude of the end effector? How do you find out roll, pitch, and yaw? So the easiest way to do that is, I want you to look at the first row, third column. Can you see that there is minus sign of theta? So if you have a rotation matrix, you would look at what the entry is at first row, third column, and then find the sine inverse of it. And that will give you the value of theta. Similarly, you will actually look at the R21 divided by R11, find out the arc tan, and then you can do R32 divided by R33. So basically, these are the elements, third row, second column, third row, third column, and then you can find out the roll, pitch, and yaw angles of that attitude. The next part which I want to talk about is Kutonians. And I'm not going to talk about Kutonians in a lot more detail because it involves a higher level algebra. But please understand, Kutonians come from a very basic principle that a rotation, a rigid body rotation can be represented at a rotation about an axis. So you can define an axis and you can define a rotation, and basically your three-dimensional rotation can be resolved. And that is called as Kutonian. So Kutonian would have magnitude, and then Kutonian would have, actually it would have four parts. There would be a scalar part and there would be a vector part. And then there are rules for Kutonian multiplication and Kutonian propagation. So think about like Kutonian is an extension of complex numbers in three dimensions. So you have I, J, K. So you are going to have same rules of complex multiplication. And then the beauty of Kutonian is that just like Euler angles, they suffer from singularities. Kutonians don't suffer from singularities. So Kutonian implementation is much more elegant. The only issue with the Kutonian is you can't visualize the Kutonian. So for example, if I give you a Kutonian, you won't be able to visualize what angles that Kutonian is representing. So what we do is, for representation, we take that Kutonian and we find out its roll, pitch, and yaw implementation, and then basically we use Kutonians or we use those roll, pitch, and yaw to actually plot. So to conclude, in this chapter, we looked at three important representations. We looked at the representation using the rotation matrices. We looked at the representation using the Euler angle, and we looked at the representation using Kutonians. As far as the dynamics is concerned, we would be studying the Euler angles, and I will give you some codes that I have already written to run in Kutonians. but MATLAB can handle Kutonians, MATLAB can handle Euler angles, and then you can go from Euler angles to Kutonians and Kutonians to Euler angles seamlessly. With that, we are done with this chapter. At this point, what I want to do is, I want to kind of tell you what my plan is, and then I want you to get ready and be prepared for what's coming next. Next chapter, yeah, question?
Professor, do those intermediate stages have any technical significance in itself?
Intermediate, basically, which, you mean arrows?
No, when it transfers from one body frame to another body frame.
So many a times, actually, I'll give you a very practical example. I was working on a problem, and actually, probably you know, you have a drone and you have a camera. Okay, drone have its own body axis. Camera has its own axis. Now, what we need to do is we need to take the picture that is taken by camera and transform it such a way that it's seen by the drone. So basically, you have a body frame for the camera that needs to be related to the body frame of the drone so that we can see in what direction the drone is going. So to relate that, you need again the rotation transformation, the transformation matrix that will take the camera frame or camera angles to the body frame. So depending upon how you are trying to resolve the kinematics, how you are trying to resolve the dynamics, you will have to use these transformations. Does that answer your question?
Yeah.
Oh.
Yeah, this is a perception, right? It comes under perception.
Yeah, it comes under perception and all. So that's coming next. So okay. The next thing what I want to talk about is with this background, we are going to study the next chapter is on the mathematical model, and that chapter is intense. So I'm gonna discuss that topic multiple times. On Thursday's class, I'm gonna give you a quick overview of the dynamical model. So basically, what are the basic equations, how those equations are derived, and what is the practical significance of those equations. And then we are going to dissect each and every equation step by step, and then program those equations inside the MATLAB and run the simulations, and then see how the model is behaving, and later take that and program the Mambo. So that is how we are going to go forward. But what I want to tell you here is if you have MATLAB, were you able to program Mambo with MATLAB or no? Mambo were able to talk to MATLAB? Yes, no? Okay, so here is something I want you to try. Let me share my screen. So if you yeah,
we apply the same for the hexacopter as well. The same Euler angles.
Yeah, you can use the same thing, hexacopter, octocopter. Okay, so I want, if you have not done it, please try to run ASB Quadcopter project, and then make sure that you are able to talk to Mambo. And there is a very simple exercise in Mambo. So there are some exercises in Parrot Mambo that I would encourage you to try, because we are going to use this when we are going to study. So as you can see, this is the method, actually the visualization of parrot mambo. If you look at, go back, you can do the trajectory modeling, you can do the basically you can open the flight control model, and you can actually put the sensors, you can do the dynamics, you can adjust the gyro biases, you can adjust the different scale factors, and then actually see how good or bad the mambo is going to perform. Now, but before we do that, please make sure that you're able to talk to mambo, or if you have any questions, I would be here for next 5-10 minutes. I would be happy to answer any questions related to setting up the mambo or programming the mambo. With that, I'm going to stop here, and then I will continue this discussion in next class. Okay, for drone blocks is sort of honor code assignment. So which means you just have to do, if you can do all the assignments on drone blocks, that would be good. But at least you should be able to program using Python, Node.js, and other programming tools, because after your first project is done, there are 8 labs. Right now we are working on the website. There are 8 labs using Telo that you will have to do. And those Telo labs would involve some type of Python programming with Yellow, then programming with object recognition, running some sort of neural network and all that stuff. For that, some exposure to programming using drone blocks would be good. And I understand that drone block does not track individual progress, but please treat that as an honor assignment. So just do it so that you are well prepared for the projects that are coming up next. So, those are, you can just submit a snapshot. Does that answer your question, Nathan? Yeah.
You didn't clarify my doubt, like why doesn't the frame move from its previous position? Like when we move, it won't be calculated from our homes, right? We'll be moving from our previous position.
Right, but the previous position is with respect to your home position, right?
Like my previous position is moving always.
So, but you can't measure something that which is with respect to moving reference. You want your reference to be fixed, and then you can find out where.
Like
So in football, if the goalpost starts moving, you can't play the game, right? The goalpost needs to be fixed.
like I'm trying to go for more on autonomous, like thinking by itself, right? I mean, when a drone moves, it should think that it moved 90 degrees from itself rather than the ground position.
Like drone will move from 90 degrees, but that 90 degrees will be different than the ground position, because your ground position may be pointed in this direction. Drone is not here. Drone can go minus 20 degrees. That is not the 90 degree for the ground position. So you need the inertial angle.
Like I'm trying to tackle the singularity. Like when we compare it to the previous position, there won't be any singularity.
Singularity will come as long as you have 1 divided by 0. As long as you take care of 1 divided by 0, your singularity will be minimal.
Sir, do you have any recommendations for 4+1?
4
plus 1 courses?
You're gonna take those next year, right?
Yeah.
Yeah, we can meet before that.
No, means I have to choose my courses now.
I don't know what courses are offered in fall. Do you know?
I know that are you teaching linear algebra for fall?
I don't know. We'll see. I will. So once fall schedule is out, I'll let you know. That's okay?
Yeah.
Because it's too early to tell, right?
Thank you so
So Professor, so do you know the password of this one, the simulator one in the jump block?
Yeah.
So can you post that on the canvas?
Can you let me?
I already sent you the email 4 days ago and 5 days ago. You didn't reply to me.
Oh yeah, last week I was.
So what's wrong with so?
I
is
was
that-
sick.
oh
Uh,
COVID?
My COVID test was negative, but I had like
The
body
COVID symptom?
symptoms. So
So you take the booster?
I'm not 6 months yet. I'm not eligible for this.
Oh, okay.
So let me here.
So I have sent you two questions.
Yeah, just a second. Let me give you. Can you try this password issue ordering 10? This is the other. I don't know. I didn't try. So
Yeah.
this is you, right?
Yes.
Can you try this password and see if it works?
Okay. Okay. Yeah, just send me. And another one is for the homework.
Yeah.
So you said so in the requirement you said that we need to like upload the homeworks and the programming assignment, right? So the homework is meaning what? It's like a quiz. The homework. Is that you mean the quiz or because
programming assignments.
yeah the programming assignments and homework.
Yeah.
What is the
So
homework?
basically, if you look at whatever assignments are in aerial robotics, MATLAB programming assignments.
Yeah, that's the programming
Yeah,
assignment.
those assignments. you should upload.
So what about the quiz?
That's the quiz, right?
No.
There are two different.
Oh, so then upload the quiz and upload the program.
For the quiz, we need to just like so how to
Take the snapshot and upload.
so we need to have the questions and like the correct or not something like that of the quiz or just I
How
have
do
a
you
certificate.
type it, right?
No. Quiz is just like the multiple choice.
Yeah. So you select multiple choice, take a screenshot and upload,
So every question.
or just put it together and then,
Wow.
or you can print it.
After that, after your completed the test, you will also get a score report of that quiz.
Yeah, score
So you
report
can
is good
score
too.
that
Oh
also.
yeah, I have the certificate. So
I
it's
too have the certificate.
yeah. So,
Yeah, we can
so,
upload the certificate.
Just the certificate.
so just upload the certificate and we don't need to upload the quiz questions specific
No quiz
questions.
question, but you have to upload the MATLAB assignment.
Yeah. I can upload
Certificate is
that.
good.
Yeah. So certificate and the MATLAB assignment, that's enough, right? Okay, perfect. Okay. That makes sense.
Yeah.
Okay, thank you, Professor. See you.
With some team or something.